Hello, are you able to hear me? Hello, are you hearing me? Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you.
What's your
Hello,
name?
are you hearing me?
Hear
Yeah,
you.
could
Could
you
you
stop
please tell
back?
us your name?
Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you.
What's your
Hello,
name?
are you hearing me?
Hear
Yeah,
you.
could
Could
you
you
stop
please tell
back?
us your name?
Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you.
What's your
Hello,
name?
are you hearing me?
Hear
Yeah,
you.
could
Could
you
you
stop
please tell
back?
us your name?
Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you.
What's
Hello,
your name?
are you hearing me?
Hear
Yeah,
you.
could you
Could you
stop
please tell
back?
us your name?
Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you. Hello,
What's your name?
are you hearing me?
Hear
Yeah,
you.
could you
Could you
stop
please tell
back?
us your name?
Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you. Hello,
What's your name?
are you hearing me?
Hear
Yeah,
you.
could you
Could
stop
you tell
back?
us your name?
Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you. Hello,
What's your name?
are you hearing me?
Hear
Yeah,
you.
could you
Could
stop
you tell
back?
us your name?
Hello, are you able to hear me?
Yes, I can hear you.
Okay, thank you. Hello,
What's your name?
are you hearing me?
Hear
Yeah,
you.
could you
Could
stop
you tell
back?
us your name?
Hello, are you able to hear me?
Hear you.
Okay, thank you. Hello, are you hearing me?
Hear
Yeah,
you.
could you stop back? Hello, are you able to hear me? Okay, thank you. Hello, are you hearing me? Yeah, could you stop back? Hello, this is invited talk session. Am I right?
Okay, thank you. Uh, okay, please just wait for us. We're gonna start late soon, and then
Hello, this is invited talk session. Am I right?
okay, thank you. Uh, okay, please just wait for us. We're gonna start late soon, and then
Hello, this is invited talk session. Am I right?
okay, thank you. Uh, okay, please just wait for us. We're gonna start late soon, and then
Hello, this is invited talk session. Am I right?
okay, thank you. We apologize for a little bit of delay due to the technical issue in this morning session. It's been a little bit delayed. And then welcome to the first session of the AFM Wednesday morning session. And then the first speaker is Devananda Mohapatra from Yeongnam University. Let's welcome the speaker. So, thank you, Chair, for the nice introduction. Very good morning, everyone present here and offline, whoever are watching this. And I want to thank you first, the organizer, for this event, and I also want to thank you them because during this difficult time they could able to handle and manage this grand event. So I want to thank you them. So thank you very much for inviting us. So if you see the title of the conference, it's Advances in the Functional Materials. So when I was invited for this, then I first thought, so I will first try to bring some of the latest materials or advanced materials so that we have been working in our university since long. So then I just try to come with the title of the work is the novel carbon nano-onion and MXene structures for energy storage and conversion application. So you can see the title and the application is very clear. So we have two advanced materials and obviously we are making some functional application. So I will be only talking about the storage and conversion in today's talk. So you are all aware of in this field of energy. So this is quite a typical diagram we used to show called the Ragini plot. So here we just try to show what are the role of capacitor, battery and supercapacitor. So capacitor basically known as the power devices which comes with very high power density because of its charge storage mechanism. And the second one, which is most famous and everybody everywhere they're using, so inside this room and everywhere. So if you see that is battery, which comes with high energy density, and but unfortunately they come with low power density. So what supercapacitor try to do, this just try to make a bridge between the capacitor and battery, so that we can accommodate both energy and the power simultaneously. So I usually whenever I talk, I just start from the little basics so that the people can catch whatever the result I will show in the couple of slides. So if you see typically there are different materials used and different storage mechanism. So if I talk about the first type is your EDLC, which is electric double layer capacitor, and the second one comes your pseudo capacitor, and the third one is your battery. So if you say EDLC, so there is no bulk storage. It is simply this physical charge separation, and this is reversible ion adsorption taking place, and no phase change happens. And the second category, which is comes under pseudo capacitor, it can be your surface redox or it can be intercalation. That depends upon the materials. So if you talk about the surface redox, the best example would be your manganese oxide or ruthenium oxide. So where there is no phase change for sure, but you will have continuous change in the oxidation states. But in case of intercalation, so you will have no phase change, but you may have change in oxidation stage, but that may not be continuous. So that is how the mechanism difference from the intercalation to the surface redox. In case of battery, so you will have phase change, so also intercalation and the change in the oxidation states. So whenever we deal with the device, we try to increase the capacitance, so which is purely dependent upon the surface area and electrical conductivity. So as I said in the beginning slide, I want to increase the energy density or power density. So for that, I need to increase the capacitance and the voltage as well. So for that, you need to take care of surface area as well as your conductivity. So if you see the typical nature of the charge discharge curve or cyclic voltammetry and electrochemical impedance spectroscopy. So if you see, in the first diagram, what I try to show you, that is your EDLC type. You can see it is a nearly square type. And if you see the pseudo-capacitor, it has redox peak, but those are not as that of your battery. As you said, the theoretically, so the peak separation is 0, and they are highly reversed. And if you see the battery, so they are irreversible, and there the peak separation is around 0.1 to 0.2 volt, or sometimes maybe more. But if you see the charge discharge plot, it is quite clear. In the EDLC, you will have very symmetric clock curve, and in the pseudo capacitor, you will have little plateau, but not just like your voltage plateau. So similarly, if you try to correlate with your electrochemical impedance spectroscopy, so for EDLC, you will get a straight line, so which is parallel to your imaginary axis. And in case of a pseudo capacitor, you will have a small semicircle, and those semicircle is because of maybe the redox functional groups or some of the redox additives. But in case of battery, you will have a clear phase change and charge transfer resistance. So most of the time you also observe the Warburg impedance. So that is at the phase angle of the 45. So some of my talk also included the doping effect. So I'll let you know what exactly doping does. So doping, basically it is started by the material physicists in the early 1980s in the semiconductor physics. So you can see the N-type and P-type semiconductor. From there, later the carbon community tried to work on that, and those doping basically arises whenever you dope any material. So basically you are influencing the properties of their intrinsic properties. So you change their electronic energy levels. So you also change their current densities, because of their change in the energy level. So you always try to change their carrier densities, and also you will also changing the surface energies of the material, and hence the properties which define your application of your materials. So if I talk about doping, especially nitrogen doping in case of a carbon material, so you expect three types of doping. So basically depends upon either pyridinic or quaternary or pyrulic. So if you see the literature so far, before we come up with our work and ideas, in the literature you can find nitrogen doping, boron doping, phosphor doping, sulfur doping. So if you see, in case of nitrogen doping, they first try to synthesize the material, whether it's a CNT or graphene or any material. Then later they try to dope it. That is a post-synthesis doping. So we call it as ex situ doping. So later, if you want to do boron doping, so you have to do the boron acid or boric acid as a dopant. So you have to implement with your carbon materials. So for phosphorus, so you have to use triphenylene phosphine or other material. But if you want to use the sulfur doping, so you have to use the sulfur powder or thiophene, which is a source of your sulfur material. But so far, before we come with our idea, there have been all the work related to your ex situ or post-synthesis doping. So making in situ doping for carbon materials, so that would be a new beginning and a new era in the terms of your carbon materials. So if you see, before I go to my work, I will just try to tell you about the carbon. If you see, this is one of the most abundant material. So if you see, this is one of the 15th abundant material in the earth and 6th in the universe. So among your hydrogen, oxygen and others. So basically this material comes with atomic number 6. And if you see, that comes with several allotropes. So not only your graphite, diamond and recently your graphene. So if you see, just because of their structure and chemical bonding, their material properties and their behavior changes. So if you start with 3D material like your graphite and diamond, so then later people start discover your graphene material, and then they went to your CNTs. It can be single wall or multi-wall. So recently, though it is discovered in 1990s, but recently people have been studying a lot about the onion-like carbon. So I'll cover some of my talk on this about the carbon nano-onion, which is called zero-dimensional material. So I'll just introduce you what is that material actually. So this material actually we have been working since long, even during my PhD time and also during my faculty period in GNEM University. So what we are working here, I'll just introduce. So this is basically fullerene family. But if you see, instead of graphene layers, which is parallel to each other and they have a 0.34 nanometer spacing between the graphitic layer, But here it just look like your onion. So where those are rings and those are separated by 0.34 nanometer. And importantly, they are sp2 hybridized carbon. And this is in the right side, you can see that is a model that we develop. You can see. So those are different layers you can just imagine. And this is in the left side, our experimental result. I'll show some of them in the next slide. So if you make a electrode, so basically you arrange your electrode material over the substrate, whether it is for supercapacitor, battery, or any other application. So if I want to arrange this material over the electrode, so I can see how it looks. So importantly, you have only exohedral pores. You don't have any typical endohedral pores like your activated carbon and even graphene. So here you can get only exohedral pores. So you can expect very high performance of the material. So in the doping, we try to do two in situ doping. So one is nitrogen doping, so another is sulfur doping. We never use any post-synthesis technique. So we directly choose the precursor in such a way that we can get the carbon nanoanion with doping. So in nitrogen doping, we just replace the carbon atom by 4 atomic percentage. In case of sulfur doping, we just changed around 4 percentage, so more appropriately 3.5 atomic percentage. So these are some of our experimental results. So if you see the sulfur-doped carbon nanoanion, which is having very unique microstructure, if you see. So as I talk about, these are your, if you see, this is your TM images. And if I talk about HRTM images at 5 nano, so you can see how those layers have been arranged concentrically each other. And these are the model we try to show that how they are connected, and you don't have any endohedral pores, those are exohedral pores. So then if you want to know whether you have sulfur or not, this is typical your redox mapping. So you can see you have sulfur in your material. So what important thing you want to find here, I will show you some of the physiochemical characterizations. So I'll talk about, if you see, this is pristine CNO. So whether you don't have nitrogen compound. So here, if you see the dry nitrogen dopant, so you have nitrogen around 4.7 nanometer. So if I talk about the pristine carbon nanoanion, it is around 218 meter square per gram the surface area. If I dope by 4%, so the surface area increased around 4 times, which is 842. So, so similarly for sulfur, which is we increased the surface area to 950 from the pristine material to 18 meter square per gram. So if I talk about more about sulfur-doped carbon nanoanion, you can see your sulfur-doped and your surface element is clearly present, and there are different surface groups. So sulfonic and thiophene groups are present. So if I talk about the Raman, which is important characteristic for a carbon material, so if you see the ID by IG ratio is quite low, 0.02, 0.72. And if you see the 2D, the band, which is a characteristic feature for a layer material. So if you see it is very quite clear, like your graphene. So you can say expect this material is behave like graphene, but not exactly graphene in terms of your microstructure and the layered information. So we just try to apply this material for the supercapacitor application. So this is a device for supercapacitor. If you see, this is pristine carbon nanoanion. You don't have any dopant here. So you can see this. These are our experimental results. So you can see your CV is quite rectangular. And if you see your charge discharge in the figure B, these are triangular and symmetric in nature. So if I calculate the capacitance, it's around 100 farad per gram at 1 ampere per gram current density. So if I need to know what is the power density and energy density, that is why in the beginning slide, I just try to show you the basics of this studies. So if you see at 1 ampere per gram, we could easily achieve around 4 watt-hour per kg, the energy density with a appreciable power density. So now the role comes in doping. So when you try to dope with sulfur by 4%, your performance increase around 3 times. So instead of capacitance 100, we got capacitance around 300 per gram. So whereas your energy density increased from 4 to is around 10 watt-hour per kg, which is quite high in terms of this material reported for the first time. So if I summarize you, I can tell you that we increased the energy density by 3 times. As I said, we not only work on energy storage, we also work on energy conversion also. We applied this material for the first time in the solar cell. So basically, more specifically, this is dye-sensitized solar cell. So in that, you can see this is a material is highly hydrophilic. We don't want any binder. So without binder, we can coat the material on the FTO substrate. And we try to make a transparent window application for this material for the first time, because graphene have been used a lot. So we try to implement this material for a transparent window application. So for the transparent window application, I'll tell you quickly the result. So this is the layer thickness is around 900 nanometer over the APO substrate, which is around 600 nanometer. So you can see the typical carbon nanotube behavior, which I shown you before. So if I talk about the result straight away, so you can see the in the DSCC, the platinum is commercially used. So in the platinum, and if you see the carbon nanotube, it's very close, but it's obviously less than your platinum, which is the best electrocatalyst in terms of your DSCC application. So if you see the optical transparency, which is important for the carbon material, so we got around 55%. So just imagine if you apply this material for a window application or integrated photovoltaic application, so you can get a transparency around 55% along with the efficiency around 5.1% of a solar conversion efficiency. So recently, when I joined this university, I applied for the proposal to the Korean government. So recently, I got my funding on this material, that is MXene, and this work have been motivated by Professor Yuri Gogoshi. So he was the keynote speaker in the first day of this conference. So this material have been discovered in Drexel University by Professor Gogoshi in 2011. So in that, they try to change from max phase to the MXene by the aluminum etching. So these are some of our unpublished results, and thankfully I got funding from the NRF government for this work. But what is the change and important thing I try to do here is this: the first top layer, if you see, this has been worked a lot. So the bottom layer, what I'm trying to do, my project is basically on. So I try to make some advanced heterostructures, bringing two-dimensional material and the CNO is a zero-dimensional material together. So I'm trying to envision, when I write a proposal, I want to know my material structure would be like this. So which is a sandwich-like superimposition of the CNO MXene heterostructures. So if I want to show you some of the results, initial results, so if you see the most characterization technique like XRD, so whenever we talk about the max to MXene, so when we remove the aluminum layer, you can see the characteristic 002 plane. So has been shifted, which is quite evident that we have been successfully get the MXene phase from the max phase. So if you see, this is titanium aluminum carbide, and this is your MXene phase after your removal of the aluminum layers. So these are some of our very basic results after I got my funding. So if you see, this is your MXene. I want to make a heterostructure with respect to CNO. So as I shown you in the previous slide, you can see it is exactly as per my envision, what I planned during my proposal. So you can see that these onions have been went inside the layers of this MXene quite clearly. You can see in your FECM images. So I want to tell you some of the microstructure aspect of this material. So if you see at the very high resolution technique like your HRTM, if you see in the figure A, so you can see this carbon nanotube completely cover your highly conducting material like your MXene in the both the ways. And if I talk about both the MXene layers have been touch each other and they have been wrapped completely, so that you can see after 5 nano, so you can see how this carbon nanotube have been well contact with your MXene layers. So we are still try to improve this material, not only from a structural point of view, from application point of view. So these are some of our basic results. So I thought for this conference as it's advanced functional material conference, so I thought this would be interesting for the audience who have been working on the advanced materials. So at the end, I would like to thank the funder when I was doing the government of India. So I was doing my PhD in IIT Bombay. So they have been funded a lot for this project. So later when I moved to Korea, so I'm very thankful to the National Research Foundation of Korea and government of Korea. So they have recently gave me the funding to work on this MXene CNO heterostructure and the Ministry of Education and University. So this is a very important slide because without them it would have been possible to conduct this research and to come here and to present and do all other research related work. So I'm very thankful for all the funders in India and South Korea. So thank you all for your kind attention. So I think I stick to the time.
Thank you very much for finishing the talk within the time.
Yeah.
And
And thank you for your nice talk. Is there any question among the audience in the online? Online, offline, maybe too. Can you check that if there is any question from the audience in the online? Maybe not. Actually, I have one very short question. Very interesting material you mentioned. But when you mentioned about the carbon nano onion shape from the TM image, in the introduction, you explained the big differences between the materials like a carbon dot, carbon sheet, and then graphene and the nano onion structure. From the TM image, how can you prove that is a fully packed onion type sphere rather than hollow just sphere or just few layer of sheets? I'll go to that result directly. Actually, I don't have what the exact microstructure what you asked. I have that. So if you see here in the figure, let us see figure D. So you have a kind of core here, which is basically a amorphous core. So it is not fully, as you said, it's not fully hollow. So at the core, it is amorphous like your diamond, and the outer layers, those have been peel off like your layers, like concentric layers. So those basically give rise to your onion-like feeling of microstructure. Actually, I don't have that exact picture, but one of the screenshot I have, you can see, if you consider this is as a core, you can see those layers have been well arranged. But exactly like graphene is two-dimensional, which is perfectly planar. This is not planar. Seems to be curvature, because material physics is more interested towards the curvature if you have any. So we have curvature here, but exactly if you talk about the layers of spherical, there are very few cases. It's not exactly you can get all throughout the things. Okay, thank you for your nice explanation. Thank you. I think we don't have no more question from the audience online. So let's thank the speaker again. And then thank you for your nice talk. And now we are moving on to the next speaker from Nanoharan Muruganda Nathan from ICE Japan. I hope the speaker is ready.
Hello?
Hello, can you hear us?
Yes.
Okay, thank you for being ready for the presentation. Now
You will use the my recorded video, or do I present now?
could you please say again?
Because already I uploaded my video. Will you use video, my video, recorded video, or do I present now?
Just wait a second, sorry. Excuse me.
Okay, means.
Would you please start and share your presentation by yourself?
Okay, okay.
Okay, let me introduce the next speaker, Nanoharan Muruganathan from Japan ICE. And then let's welcome the speaker. And then
Good morning. Good morning, everybody. This is. Okay, 1 minute. Sorry. 1 minute, 1 minute. Okay, I'm sorry for the delay. Okay, I am Manogran. I will present our work of high performance graphene devices, especially nano-electromechanical devices, and the detection of silent voice from thunderclouds. Um, Thank you, Chairman, for this kind introduction. I am from Japan Advanced Institute of Science and Technology, Japan. So today I will be discussing three works. First one is graphene nano-electromechanical switches, which is for high performance devices, and second is graphene nano-electromechanical switches for single CO2 molecule sensing purpose, and then I will move on to the graphene electric field sensor to sense the thunderclouds movement in real time. Okay, so first question is, why do we need graphene for nano-electromechanical systems? The reason is it has very good electronic property like high mobility, high conductivity, all those things. But apart from that, it has high carbon to carbon bond strength as well as the Young modulus of 1 terapascal. And it can withstand up to 20% tensile strain without any damage to it. So these are very impressive property for nano-electromechanical systems. And apart from that, it has high surface to volume ratio. That means that whenever molecule adsorbed onto it, it can easily affect the graphene conduction property. So we can use it as a sensor material as well as. These properties are very attractive for nano-electromechanical system as well as single high performance sensors. Okay, so we proposed a new graphene nano-electromechanical switches as shown in this one. This animation shows that when it is in top positions, these cantilevers, the source cantilevers and drain cantilevers are not touching in this blue color. But when they are pulled down to the bottom graphene, then there is a current flow from the source cantilever to drain cantilever through the bottom graphene. So because they will have the contact, electrical contact through the bottom graphene. So this gives the ideal advantage of low leakage current ideally. So if we compare this switch performance with the typical MOSFET performance, the MOSFET performance is shown in this pink color lines. Horizontal axis is gate voltage and vertical axis is drain current. So in the MOSFET, even in the off state, like around this region, it will have leakage current. But in the case of graphene nano-electromechanical switches, they have physical isolation in the off state as shown in this schematic diagram. So they will have low off current. When they are pulled down, then they will have the high current flowing through the cantilevers. So this is an ideal switch for the future devices. And to realize this switch, we divided our works into three parts. So first step is to demonstrate two terminal switches. That is, we have a suspended graphene ribbon clamped at the two metal electrode as shown here, and we have the bottom electrode as shown in this AU electrode. If we apply the voltage to this electrode, then this graphene will be pulled down, and then current will flow from this part to this part. That is top electrode to bottom electrode. By that one, we can understand that whether we pulled in or not pulled in and pulled out operations. So we fabricated this device, and this is the optical image of our device. Like this is top electrode and bottom electrode, and this is AFM image. Now as shown in this figure, at 1.8 volt, like if we increase the voltage of bottom electrode to 1.8 volt, then as shown in this insert, the suspended graphene is pulled down at this voltage. Then when we apply the high voltage, it is pulled down very much, and when we reduce the voltage, then it came out. That means that again this cycle went back to this one, so it pulled out again. We could repeat this one for few cycles. And what is important thing is we could achieve this operation at 1.8 volt, but if you take the silicon NEM switches, they needs at least 20-30 volt for this dimension. That is the main advantage of graphene. Okay, and to proceed further, to realize many cycles, like only few cycles we achieved in this first step, and second step we wanted to achieve at least more than 100 cycles. So for that purpose we modified our device structures to this one, doubly clamped beam, but we have the switching electrode as this one, but with chromium oxide naturally formed. So we fabricated this device for this is also two terminal switches. Like when we voltage we supply to this gate, then after the certain voltage, threshold voltage, then this graphene will be pulled up and they will have the current flowing through this one. And this is cantilever, suspended cantilever. We fabricated these devices, like this is double clamped beams and this is cantilever type. We could see that clear pull in and pull out operations for in these devices. This is for doubly clamped beam and this is for cantilever type. And we could achieve within around 5 volt pull in operation. In these devices we could achieve more than 100 and 150 cycles of operations. Beyond that, this chromium oxide and graphene had a bond and we could not recover back. So then we moved on to our third part. Okay, now I come to this part. Why this structure is very important? The reason is graphene to graphene bonding is happening through the van der Waals force, as you discussed in previous discussion and yesterday's discussion also. The graphene bond is the layer 2 interlayer bonding is dominated by this van der Waals interaction. So they will not make a permanent covalent bond. That's the main advantage of this one. And in this structure we can see that it is 3 terminal. That is, you have one source electrode, drain electrode and bottom electrodes. When we apply the voltage to the bottom gate electrode, then this cantilever will be pulled down and current will be flowing. But when we reduce the voltage to the gate voltage, then it will be pulled up. Then there won't be current flow between this terminal to this terminal. In real time we want a switch like this one. We want to establish the connection between these two through the third terminal. This conventional mass industry is based on this concept. So for that purpose we slightly modified this cantilever structure to this one. Okay, so maybe you can follow this structure. So instead of cantilevers we change it to the doubly clamped beam, and we have air gap here, and this is source graphene and this is drain graphene. The reason to change to the doubly clamped beam is, in doubly clamped beam we have high mechanical restoring force, so we can easily achieve the switching operation compared to the cantilevers. That's the main reason to change to this structure. And we have the 2D hexagonal boron nitride dielectric as shown here, and bottom gate graphene. So if you notice this one, all the main components are drain, source, gate dielectric and gate electrodes are consisting of only 2D materials. So this is more it is possible to use in the flexible electronics easily. Okay, this is a summary of our device fabrications, even though it is a really complicated one, so I make it schematic explanation for how we fabricated this device. Okay, first we transfer gate graphene onto the gallium arsenide substrate as shown in this one. So the insert shows the cross section view. Then after that we transfer the gate dielectric using that is hexagonal boron nitride. Then we deposited the source graphene. Again, this is achieved by 2D transfer systems, which is mechanically exploited graphenes and HPNs are transferred onto this substrate. Then we deposited sacrificial SiO2 layer as shown in this one. Then if you see the cross sectional, we have the bottom graphene, hexagonal boron nitride, and of course source graphene. Above that we have sacrificial SiO2 layer. Then we transfer the drain graphene as shown in this one. Then we made the electrode contact. That is, this is drain terminal and source terminal is consist of connected by this one, and this is gate terminal which connects the bottom graphene. Okay, so as shown in this one. This, okay, if you notice carefully, here we had the sacrificial SiO2 layer that is shown in this one, and we removed this sacrificial layer at the last. So we could achieve the suspension of this drain graphene from the source graphene, and we can maintain the air gap here. Okay, this is it's our measured results. Like initially we could achieve the pull-in operation at around 7.8 volt, and after few cycles then voltage, the pull-in voltage reduced to the around 5.3 volt here around this part. Then if we see the if we reduce the voltage, that is when we apply the voltage to the gate electrode, then this graphene is pulled down, and when you reduced, then this graphene will go up. So that is called pull out operation. So the graphene is again the drain graphene goes back to this one. And what is the remarkable achievement in this one is we could achieve the substitute slope of 10.4 millivolt per decade, which is really very high performance. And one of the limitation of our devices is we used gallium arsenide to avoid the buffer HF etching, but usually gallium arsenide substrate has more leakage current than the SiO2 substrate. That's why we had this leakage current. Otherwise we could achieve more than 5 orders, 6 orders pull-in pull-out ratio, that is ion-off ratio. Okay, so to summarize our this three-terminal switches, I can explain this animation diagram. So this is the suspended drain graphene, and when we applied the gate voltage, then graphene was pulled down to the source electrode, then current flows through this one, then source to drain connection is established, and when we reduce the gate voltage, that is bottommost graphene, then this graphene went up. So this is an idea switch, like you as we have seen in the previous measurement result, we could achieve very sharp switching operations, that is around 10 millivolt per decade. This is really remarkable in all the 2D systems, and this device can be explored for the power saving operations in real time operations. Okay, now the question is, okay, what are the other application, or how can we explore this NEMS technology for sensing operations? That's next question. So for that purpose, we explored this suspended graphene, because the suspended graphene has the less interaction with the substrate. So we wanted to explore for the sensing purpose. So to explain that one, first I will briefly explain our DFT simulation results. This is a suspended bilayer graphene. When single CO2 molecule adsorbed onto this one, it affects the electron density distribution throughout the channel as shown here. But if we have, this is with SiO2 substrate, if we have SiO2 substrate, then SiO2 substrate will have some defect. Even any substrate, whatever substrate we use, that will have some defect at the surface or internally, that will affect the graphene's electron density distributions. So if single CO2 molecule are adsorbed on that one, this sensing capability is smeared out by the defects in the substrate. But if you have suspended that one, suspend the graphene, then you can overcome this issue. So for that purpose, we fabricated a suspended graphene as shown in this one. The length is 300 nanometer, width is 1.1 micrometer. Okay. Another one thing we wanted to do in this device structure is, when we want to accelerate the sensing operations, because if we are able to sense only the few molecules over the hours, then it is not useful for real time. So we wanted to accelerate. For that purpose, we explored this bottom gate voltage, that is we applied the bottom gate. But if you apply the bottom gate voltage, then the graphene, the suspended graphene, if you fabricate like this, it will be pulled down. So to overcome that issue, what we did is, first we fabricate double clamped beam, then pull down to this bottom gold electrodes. Carbon to gold electrode will have very good bonding, so they will permanently stick here. Due to the some tensile strain in this one, they are very stiff, and when we apply voltage again to this one, it will not be affected. I will explain that importance of the backgate voltage in the next slide. Okay, next slide. Okay, so in order to understand the details of this suspended graphenes and its impact, we further did some DFT calculations with van der Waals force, because taking care of van der Waals interaction in DFT is really tough, but otherwise for sensing purpose we have to take care of it. That's the main thing. So we did that one. By that one, if you see the suspended graphene and single CO2 molecule adsorbed onto the graphene, we can see that single CO2 molecule really disturbs or certain range. We found out from this simulation around 5 nanometer of the channel is affected if single CO2 molecule is absorbed, and if you analyze the potential energy, this potential energy is much higher than thermal energy. So even single CO2 molecule adsorbed onto the suspended graphene, it will change the resistance value. With this understanding, we went into the device measurement, that is sensing measurement. So this is CO2 sensing measurement. Like as I explained, we fabricated this suspended graphene nanoribbon. Okay, this is AFM image, like top electrode, bottom electrode, suspended graphene. Then if we measure without applying the backgate voltage, that is this voltage, substrate voltage, we could not see any change in the resistance. But when we apply the gate voltage to 15 or minus 50, then if we analyze the resistance changes in the channel over the time in the CO2 due to the CO2 molecules in the chamber, we could see the clear steps, like sometime increase or sometime decreasing also. So we could see it. We further analyzed these data using statistical analysis. Then we found out that we have the two peaks. One is 61 ohms and minus 61 ohms. So we attribute these steps to the single molecule adsorption or disruption. As we discussed in this one, each single CO2 molecule will block the 5 nanometer of the channel, and disruption will also release that 5 nanometer channel. So if resistance increases, then it is attributed to the single CO2 molecule, but resistance decreases means then disruption, that is molecule is leaving the graphene surface. And we found out from this DFT calculation that these CO2 molecules are adsorbed by the van der Waals bonding, and that is species option. To explain that one, I will we did molecular dynamic simulation using semi-empirical method. So when we apply the backgate voltage, then the molecules hovering over this free surface, some molecules move on to the graphene, and once it adsorbed onto the graphene, they hover over the graphene surface. They don't escape, as you see here. Because, and of course, as I already mentioned, this is due to the physics option, that is physically absorbed, not chemically absorbed. But when we don't apply any gate voltage, then we found out that whatever the molecules coming and they were leaving the surface, they were not able to hover over the graphene surface. This is due to the potential hill formed in this device, that is this as shown in this diagram. When the molecule is far away, it has low potential but high kinetic energy. When they move on to this nearer to the graphene, then due to this applied backgate potential, they form some kind of potential barrier as shown here. Then the potential barrier is increased and kinetic energy is reduced and precipitation happens, then these molecules are trapped over here. Then they cannot escape from this one easily. Due to this one, we could achieve the quickly single molecule adsorption in this our devices, like with the gate voltage, positive or negative voltage. This voltages makes a potential barrier and it captures the molecules onto the graphene channel. So we could see the response in few 10 seconds to few hundred seconds easily. That is very remarkable with single molecule adsorptions. This is really very good for the sensing of very very low concentration molecule like formaldehyde, like very VOC molecules, those molecules in real time. Okay, so now I will move on to our third part of the discussion, that is electric field sensing using graphene. The reason for this work is, as you know very well, thunder causes really huge damage to the properties, like as shown in this impressive pressure picture. So this lightning damages the properties, but also it kills the people also. So even though this is very economically it is making huge loss, we have to find sensors which could detect the movement of these thunder clouds in well ahead, like maybe at least 30 minutes before we need to understand it. Then we can give the warning to the real-time warning to the ground people, because the satellite forecast, that weather forecast, cannot accurately detect the movement of these thunder clouds at present. We need some real-time monitoring. That is, if the thunder clouds are moving, then we have to detect from various places in the ground how far this thunder cloud and what is the speed of its movement. All those things we need to understand. So for that purpose, we want to explore the graphene, because graphene is highly sensitive material due to its high surface to volume ratio. And another thing is the electric field strength is inversely proportional to the distance. So this is our collaborator Ottawa company result. As you see here, like from the center, that is center of the thunder cloud, to the, if you go far away, like 4.5 kilometer, 8.5 kilometer and 15.5 kilometers, how the electric field is changing with respect to time. This was sensed using electric field mill sensors, that is as shown here. It will have a DC motor and a capacitive kind of detection is carried out in this one. If you see here, like there is at the origin we can sense the electric field sensor quicker, but if we go away from the surface in center of point, then we can say that there is some delay, like 30 minutes or 1 hour delay in this one. That means that thunder cloud will come later. So if you could sense this thunder clouds far away, like 10-15 kilometers away, 30 minutes ahead, with cheap device, then it should be better. The problem with the electric field mill sensor is they are bulk and they have motor. Due to the motor wear and tear, and they need power supply, and it has to be installed on the roof. It is big actually, that's the thing. So we need a sensor which is cheaper and sensitive, very high sensitive, and it can detect the movement of the clouds also. So for that purpose, graphene is the best candidate. So to explore the graphene, we wanted to utilize traps in the SiO2 surface. Like if we have silicon and silicon dioxide interface like this here, then we will have the traps in the SiO2 layers, not only in the interface and in the SiO2 layer also. So when the electric fields are applied, then those electric field will make the traps to be charged or decharged. That's the main thing. By utilizing this charging and decharging, we can sense the electric fields. So we fabricated the device, and this is typical gate characteristics of our graphene device. This is the optical microscope image, like 5 micrometer length graphene nanoribbon and width of 6 micrometer. And we did the negative and positive electric field sensing measurement. So as shown here, when we apply the electric field, and then we could clearly see that there is a change in the current. This is okay, sorry. Whenever there is a change in the electric field, then the drain current will change accordingly. If the electric field increases this way, then drain current decreases. When electric field increases, then it will go this way. Based on that one, we detected the positive and negative electric field as shown in this one. So we could clearly see that for negative electric field the change is increasing, for positive electric field it is decreasing. So for the first time we have sensed both the positive and negative electric field, and we are further improving these device structures, and further measurements are going with along with the company works. Okay, so now let me summarize our my discussion today. We fabricated and reported the 3-terminal all 2D GNEM switches, and we demonstrated 5 millivolt per decade switching speed. That is very remarkable to have the low off current as well as the high speed operations. And we overcome the restriction of the graphene to the gold bond by using graphene to graphene van der Waals bonding. And we utilize our GNEMS technology to detect the single CO2 molecules in our suspended graphene, and we could sense single CO2 molecule adsorption and disruptions. That is, and it was very high speed enough to in within 10 to 100 seconds we can sense the single molecules adsorption and disruption. And we fabricated the graphene electric field sensors, and we could sense the ambipolar electric field in our graphene. Thank you very much for your kind attention. Okay, these works are supported by JSPS Kakeni projects as shown in these numbers, and JST, Japan Science and Technology funding from COI and A-Step tryout funding, and Ottawa Electric Company Limited. Thank you very much for your kind attention.
Thank you, speaker. Is there any question from the audience online? Is there any question from the audience online? Okay. Actually, I have one question. A very, very short question. You mentioned about 3 parts in your presentation. In the first part, me.
Yes,
Yeah. In the first part, you mentioned about the 3-terminal the switch system.
yes.
And in that part, when you apply the voltage to the gate, then the graphene sheet can touch down the bottom part, right? Is that true?
Yes, yes.
But you mentioned that there is no leakage current, and then the tunnel voltage can make a very like a reproducible device. But I have just one short question: is that the cycle property? So have you repeat the measurement like pull down up and pull down up like a cantilever? Is it reproducible and then cyclable, like without any hysteresis like that?
Okay, that is recently we have finished that work. Yes, we could. Okay, we could do it. At least hysteresis won't be zero, very small. Now we have realized that work. So maybe soon we will be submitting that result to the journal. And of course, we not only one device, like we fabricated many devices, we could achieve this pull-in pull-out operations with small hysteresis voltage in many devices.
And is there any question, more question from the audience online? Okay, if not, let's thank the speaker again. Let's move on to the next speaker. Because we are.
Thank you, sir.
Thank you very much again. finished the talk very on time, so we are now ready to listen to the third speaker. The third speaker is Liao Yongwen from Westlake University, China. Can you hear me, please? Liao Yongwen, are you there? Would you please answer to us? I think I saw the name among the attendees. Would you please turn off the silence function? We can't hear you. Would you please turn off the mute mode? I think you are now in mute mode. Okay, I think because the technical issue, we cannot get any response from the Liao Yongwen. So let me contact to the next speaker. Chang Jian, are you there? I think the first speaker, Chang Jian, is not ready. Maybe the speaker believes the schedule is properly progressed. Okay. Let me ask again. Liao Yongwen, are you there? Can you hear me? Would you please turn off the mute mode? Okay, because we shouldn't delay anymore. So let me introduce the next speaker. So we can, once we have a response from the both speakers, Liao Yongwen and then Chang Jian, we can move on to their talk soon. Sorry, I think due to the technical issue, it's been delayed. So okay, because we shouldn't wait our time anymore and no more. So let's move on to the next speaker. We can switch the schedule of the presentation. The next speaker is Arang Jang from Semyeong University, Korea. Professor Arang Jang is going to talk about gas sensor for selectively detection of hydrogen sulfide in mixed gases at room temperature. So let's give him a couple of seconds to be prepared. Sorry, due to the technical issue, the connection is not functioning well. So we are sorting out the technical issue. I think the screen is not properly shared. Okay, I think we sorted out the issue. Let me introduce the speaker again. Due to the technical issue, we cannot contact to the Liao Yongwen and then Chang Jian. So let's move on to the next speaker, Arang Chang. We can just switch the schedule. So Professor Arang Chang is from Semyeong University. He's going to talk about the gas sensor for selectively detection of the hydrogen sulfide in mixed gases at room temperature. Let's welcome to the speaker, and then let's listen to his presentation.
Good morning. I am Arang Jang, and thank you for giving a chance to present in conference AFN conference 2021. I will introduce my research progress briefly about gas sensors. As you know, long time ago when miner went to coal mine, they need canary to detection of toxic gas like carbon monoxide or some methane, because canary is very sensitive. So if carbon monoxide or toxic gases exist, they are easily dead. So if canary is dead, coal mine is escaped coal miner escaped coal mine, so they can save their life. And as you know, the canaries nowadays the canaries are in need in our normal life, because gas accident is happened in our everyday lives like this. So we need a portable canary that is a gas sensor. And gas sensor market is growing increase, because gas sensor used as a prevent gas leakage accident. In addition, they can also use the gas food safety or medical diagnostics. There are many types of gas sensor like that. Photoionized detection type of sensor and electrochemical and semiconductor type sensors. Among that, there are many advantages or disadvantages depending on the gas type of gas sensor. Among that, I choose semiconductor type gas sensor because low price and small dimension, so you can integrate it the gas sensors. Semiconductor type of gas sensor has advantage like this. There are low price and mechanically robustness and small dimension, so we can integrate the gas sensor on small chip, look like this, but they use the metal oxide as a sensing material, so they need heater to detection of gas molecules. So they need a heater, and the meaning is they need high power consumption. And semiconductor type of gas sensor can distinguish the reducing gas or oxidizing gas. But among the reducing gas, something like nitrogen dioxide or ammonia, they cannot distinguish the what type of gas. So the meaning is that low gas selectivity problem is happened. And previously I already explained the problem is semiconductor type gas sensor is they need high power consumption because of the heaters. So I test the gas sensing property depends on the temperature. As you can see, at low temperature, the gas sensing is gas sensing properties are going to poor, and then they cannot refreshing like this. On high temperature, they can detect the gas, but as you know, if we make the micro heater, there has many problems, some leakage problem or stability problem. So first, because of that, I want to make the gas sensor with working at room temperature. So I chose the two-dimensional materials because two-dimensional material has a high conductivity and they are easily surface modification and large specific surface area. So in this presentation, I used the molybdenum disulfide or graphene and copper sulfide. This is the first topic of this presentation. When I when I check the molybdenum disulfide, I can know there are two type of page look like this 2H page and 1T page. 2H page is a semiconductor page and 1T page is a metallic page. And as you know, 1T phase has a very large catalytic effect than 2H phase. So we expect gas sensing property also very larger than 2H phase. But 1T phase has one problem, that is very unstable. So we're looking for some literature and you can find phase locking process. When you cross the zinc oxide on 1T phase MOS2, under the harsh condition, the 1T phase is maintained. So we cross the zinc oxide on MOS2 and we locked 1T phase MOS2 like this. Yeah. If we are not original 1T phase case, if we doing the flash annealing, then meaning is flash annealing is just to increase the temperature using the lamp. If we doing the flash annealing, many parts of 1T phase MOS2 going to 2H phase, but phase locked 1T MOS2 case, they are maintained the 1T phase. So we find 1T phase 1T phase MOS2. If we use the 1T phase MOS2 material as a sensing material, maybe around 100% better sensitivity of NO2 gas than 2H phase MOS2. So we can make the high sensitivity MOS2 using phase locked 1T phase 1T MOS2. And this is the second part. We wanted to check the gas sensor using the commercialized. We check the commercialized gas sensors. There are many gas sensors. You can buy many gas sensors like some hydrogen sensor or carbon monoxide sensor or methane, ammonia, something like that. And then we bought many type of gas sensor and we apply nitrogen dioxide. As you can see, most of gas sensor is reacted to nitrogen dioxide. That meaning is the gas sensor cannot distinguishes the gas. So I want to find out I want to increase the selectivity of gas sensors. Selectivity chemicals selectivity of gas sensor. As you saw, I'm looking for some material and I found Ag2S material is a very high binding with acetone. So we synthesis Ag2S nanoparticles using ultrasonic irradiation method. It is a very simple method, and you can synthesis very easily Ag2S nanoparticles. And we check the disperse of Ag2S nanoparticle on various substrate, something like dipping method or spraying method. And we find the spin coating method is a very simple method, and then this is a well working look like this. We just spin coating the Ag2S nanoparticle solution on graphene, and as you can see, very uniform Ag2S nanoparticles is dispersed on graphene very uniformly. So Ag2S nanoparticle decorated graphene case, the acetone sensitivity is a very acetone sensitivity is increased like that, about 660%. But ethanol and hexane case, the sensitivity response is not increased like this. So you can realize the acetone sensitivity gas sensor using Ag2S nanoparticles. This is a DFT calculation, and then we also find out Ag2S nanoparticle and acetone has a very good high binding energy. And second one is I choose the graphene 3D foam as a sensing material. This is a Jameson Tools group's result, and they make the graphene foam on Kapton film using laser describing. And this is a very easily make the 3D foam graphene on Kapton film. So using this method, we also make the graphene foam on different polymer. It is not published yet, so I cannot explain detailedly, but we used another polymer and then many metal salt. You can make the 3D graphene foam. At the same time, we can decorate the nanoparticles look like this. And we can decorate many nanoparticles on 3D graphene foam easily. And we also check the metal or metal oxide nanoparticle is well decorated on graphene using XPS result. And we check the gas sensitivity of various metal decorated graphene 3D foam. As you can see, depends on the metal, the sensitivity also changes look like that. Ammonia case, PT decorated graphene has a very good, showed a very good response property, but as you can see in toluene case, the PT decorated graphene could not respond like that, but zinc decorated graphene has a very good, showed a very good response result. So using this result, we are looking for the adapt material to depend on the gas molecules. And lastly, we check the commercialized gas sensors using mixed gas. Until now, we use the we test the gas sense using single gas exposure condition, because the reason is this: we bought commercialized gas sensor and we supplied mixed gas like that. Then we mixed hydrogen gas with methane and propane, but gas sensor cannot distinguish the hydrogen. Yeah, that meaning is the commercializers cannot distinguish the gas if the gas is supplied mixed if mixed gases are supplying. Yeah, so we want to find out the way. How can we distinguish the target gas? And we are looking for the some uh, mm, we are looking for the some solution like that. As you know, the percolation threshold is exists when we deposit a film. When we deposit a film, first time the film is not generated. The looks like this. Island is generated like that. But after some threshold, percolation threshold, the continuous film is generated along like that. So that meaning is if uh, the deposition thickness is very thin, maybe under the 4 nanometers, the current is not flow because continuous film is not generated. But something over, if over the percolation threshold, the current is start to flow. So if we make the island uniformly, and then the island is near the percolation threshold, we think we can make the selectivity gas sensor because gas sensor. Among the material, the kappa is one target material because kappa oxide, if kappa sulfide from the kappa oxide has a very huge volume expansion factors, that means if we make the kappa oxide nanoparticle and then we transfer the kappa sulfide, the volume is expanded about 50%. And so we make the kappa oxide nano island on various substrate. And then we supplied many gas to kappa oxide island based gas sensors. As you can see, when we expose hydrogen, nitrogen dioxide, and ammonia, the kappa oxide cannot flow the current. As you know, kappa oxide is very easily changes under various gas conditions. But kappa oxide, if we choose the some specific distance of island, under the different gas condition, the current is not flow. But in the mixed gas, if hydrogen sulfide is exist, the kappa oxide is changed to kappa sulfide. Kappa sulfide is a very good conductive material. So the meaning is if we make the kappa sulfide continuous film, the current is a flow. So if we expose the kappa sulfide, hydrogen sulfide gas, the current starts to flow along like that. That meaning is you can detect hydrogen sulfide on the mixed gas condition. So we check the TEM like this, and then we can find this TM images we make the kappa oxide island. As you can see, the kappa oxide island is not make the continuous film. The island is exist, so that means the current cannot flow under various gas condition, mixed gas condition. But if hydrogen sulfide gases exist in the mixed gas, the kappa oxide is changed to kappa sulfide like that. During the change the kappa oxide to kappa sulfide, the volume expansion is exists about 50%. So the continuous film is generated, And then, as you can see, the current can, previous slide, you can see the current is a flow. So using this population threshold and volume expansion, we can make the hydrogen sulfides selective gas sensor. Until now, I explained the gas sensor to operating at room temperature and enhancement of gas selectivity using AG2S nanoparticle decorated graphene and many different type of nanoparticle decorated graphene. And then I used the copper oxide in Ireland, and then I found the hydrogen sulfide selective gas sensor using population threshold and volume expansion properties. Thank you for attention. And yeah, thank you.
Thank you, Speaker Professor Arang Chang. Is there any question from the audience online? Maybe not, because I cannot hear any question. Actually, I have very short question. Whenever I heard about the gas sensing, I wondered how we can reproduce the device and recycle the device, because this is not just durable device. So if we want to use this device again, we may need to remove the sensed gas inside the device to recycle the device, reuse the device.
Yeah,
how you can reuse the device, how you can remove the attached gases.
Yeah, so as you know, semiconductor type of gas sensor, we use the heater. Yeah, so at the high temperature, maybe 300 or 400 degrees C, the gas molecule is detached from the sensing materials. But in this case, a room temperature case, it is very hard to detach the gas molecule from the sensing material. So the last topic, the hydrogen sulfide sensor case, that is just a one-time sensor, but it is a very cheap. And then if we use the graphene-based gas sensor, we applied current a little higher, and then the jolting is generated easily and very short time. And then you can detach the gas molecule from the gas sensing materials. So we have a two-way. One is a very cheap sensor, and one is using high current density, high power consumption. Yeah. So as you know, we are not found out the perfect sensor, but yeah, we find out a way, and then we looking for the more best way. We still looking for the best way.
Thank you for the answer for the question. Is there any more question from the audience online? If not, okay, let's thank the speaker again. And then due to the technical issue, we changed the schedule, and then we now got in touch from the Changjian. Before we move on to the Changjian, let me ask again. Liao Yongwen, can you hear me? Are you there? An attendee named Wen in the attendee list. So I believe Liao Yong Wen is in this session online. Probably the connection is not good enough. Okay, okay. Time is flying. Okay, let's move on to the next speaker, Chang Jian. Chang Jian, can you hear me? Just a minute ago, we got a message from the Chang Jian that Chang Jian is ready for the presentation. Can you hear me? I think recently when we do this kind of hybrid conference, the overseas speakers sometimes get in trouble in the connection. Okay. Let me check again. Liao Yongwen and Chang Jian, are you there? Can you hear me? 네. Okay. I think on Monday we had another speaker, but due to the technical issue, we wasn't able to invite another speaker named Sabu Thomas. Are you there, Sabu Thomas? I think according to this updated agenda list, Sabu Thomas is scheduled to present now in this session. Okay, I think, yeah, due to the technical issue, we may need to take a break for 5 minutes because we got the message from the Chang Jian was being ready, but still we have some technical issue. We may need to take a 5-minute break. See you in 5 minutes. Sorry, there is another announce. Due to the technical issue, we are still keeping in touch with the three remained speakers, but we are not able to get any response from the speakers. So we probably need to continue whenever the speakers are ready. So please bear in mind, and then please stay in the Zoom session room, and then we're gonna announce again when the speakers are ready. Sorry for delay and then technical issue. Sorry, audience. There is another announce that we will try to contact to 3 presenters in this session, Liao Yongwen and then Chang Chen-yan and Sabu Thomas. But unfortunately, due to the technical issue or the overseas internet connection, we were not able to get any response from them. So unfortunately, we're gonna close this session, and then there will be another session from 11:30 Korean time, like in 40 minutes. Please attend in that next session. So thank you for attending in this session, and then now we are closing this session. Thank you for attending again. Hello, hello.
Okay. Hello, I'm this. I'm chair. This season. My name is Yunting Chan, and let's welcome the first speaker. The name is Toniski S. Kara. His topic title is the nerve correction inhibitor on the base of actin degradative. Let's welcome.
He has submitted a PowerPoint presentation, and he's not currently here. Uh, could the person presenting this topic, if the person is in the Zoom, could you please chat? Hello? Okay, the person is not here, so unfortunately we would have to skip this person, because although he submitted a PowerPoint presentation, it does not have any sound. Unfortunately, however, you will still be able to view his presentation via YouTube when he uploads the version with sound in it. Okay, now we will move on to the next presentation, given by Mr. Mir Mohammed Hafiz Shahabuddin. And the topic is influence of dope solution formulation and spinning conditions on the morphology of PSDIF8 mixed matrix hollow fiber membrane for gas separation. He has submitted a video which will be played now. Please wait a few minutes. The person kind of confused.
Hi everyone, I'm Mior Mama Hafiz and I'm a postgraduate student from University Science Malaysia. I will be talking about the influence of doped solution formulation and spinning conditions on the morphology of PES ZIF-8 mixed matrix solar fiber membrane. This membrane is fabricated for the application of gas separation such as carbon dioxide and nitrogen gas mixture. Illustrated here is the hollow fiber membrane. It is cylindrical in shape with a hollow center, which we call as the lumen. To separate gases, the outer skin layer must be dense, followed by porous substructure. This is because the overall process obeys the solution diffusion mechanism. Meanwhile, the lumen site must be perfect in circular shape to avoid any mechanical strength issues. To achieve such perfect structure and morphology is a complex work. There are reports available, but they are pretty much contradicting with each other. That is why a study is necessary, because the spinning conditions and also the dope formulation is very unique and specific for any kind of polymer. So this study will be divided into two parts. The first one is to investigate the influence of doped solution formulation and spinning conditions on the morphology of the PES hollow fiber membrane. PES is short form for polyethyl sulfone. Appropriate dope formulation, air gap, and ball field flow rate will be identified from this section. Hypothetically, formation of dense layer is a result of delayed demixing, which can be achieved with high polymer concentration, volatile additives, and also long evaporation time. Meanwhile, the second part of this study will focus on the fabrication of mixed matrix hollow fiber membrane, where ZIF-8 will be included in the polymer matrix. ZIF-8 will be included at 10 weight%, and the morphology of the mixed matrix hollow fiber is also the main interest of this study. ZIF-8 is included to reduce the trade-off effect between the selectivity and permeability, which is always associated with polymeric membrane. Firstly, we identified the critical concentration of the polyethyl sulfone doped solution. Critical concentration is highly important because it will be a good indicator in the formation of dense outer skin layer. So any formulation of the hollow fiber membrane in this study will be made based on the critical concentration. We identified that 29 weight% polyethyl sulfone is the critical concentration in our study. Also, the hollow fiber will be produced by using the hollow fiber spinning setup as shown in the figure down there. And also the video of the process is provided. All membranes produced will be freeze fractured and will be analyzed using SEM to view the structure of the membrane as well as its dimension. The membrane is prepared by dry wet phase inversion, where it will flow through the spinneret extruded through some air gap, which is where the dry phase inversion is taking place. As the membrane reaches the end of the air gap, it will meet the coagulation bath. This is where the wet phase inversion will take place. In this process, the already formed dense outer skin layer will suppress the movement of solvent out of the membrane. This will form the sponge-like structure in the middle part of the membrane. The membrane collected in a take-up drum will be immersed in the eye water for about 3 days. It was followed by the process of drying the membrane for another 3 days before any analysis could take place. These are the findings of this study. Firstly, we compared the doped solution concentration. We used 29 weight% and 33 weight% PES to fabricate the hollow fiber membrane. As you can see here, both hollow fiber membrane produces similar asymmetric structure. They have outer dense layer followed by voids beneath the outer dense layer, and following that is the sponge-like structure. If we're taking a look from the lumen side, it also has dense layer but with teardrops beneath the skin. The only difference here is that the lumen side in 33 weight% hollow fiber membrane is not regular in shape. This is mainly because of the viscosity and also the buckling mechanism as discussed by many other authors. Meanwhile, we can see that the inner teardrop structure is longer relative to the one beneath the outer skin layer. This is because the lumen exposed to the bore fluid much earlier than the outer part. With that, we concluded that 29 weight% polyethyl sulfate is suitable to be produced as hollow fiber membrane in this study. The thickness of the dense layer is also an important measure because too thick of the dense layer will suppress the permeability of the gas molecules and reduces the permeability reading later on. So with 29 weight% PS, we varied the air gap and bore fluid flow rate. In this study, we varied from 5 to 20 cm of air gap, while the bore fluid flow rate was varied between 4 and 5 milliliter per minute. For 29 weight% PS in NMP, we can see that the structure or the morphology of the membrane is similar as to the one mentioned earlier. However, with varying air gap, we can see that the lumen is now begin to have better perfect shape as we use 15 cm of air gap and above with the bore fluid flow rate of 5 ml per minute. Meanwhile, when we included ethanol into the dope formulation, we can see that at the range of air gap studied and also the bore fluid flow rate studied, none of the membrane produced were imperfect or circular shape of the lumen. However, the main difference with the first one is that there is no voids beneath the outer skin layer. This is probably because of the viscosity, and the lumen is because of the instability during the production of the membrane. For your information, both dry and wet spinning process resulted in phase inversion of the polymer solvent non-solvent ternary system. Well, these processes are responsible in the formation of the asymmetric structure of the hollow fiber membrane. But in the case of ethanol, the demixing process is too slow, thus less of voids in the structure. So readings were translated into graphical representation, and we can see that the trends are pretty much similar for both formulations. For 29 weight% PS solution, and when we included ethanol at 9:1 ratio of NMP to ethanol, both shows that as the air gap increases, the dense layer thickness also increases, while it is inverse for the dimension of the membrane, which means the thickness of the membrane. So we found out that 15 cm of air gap and 5 ml per minute of bore fluid flow rate is suitable to develop our mixed matrix hollow fiber membrane. So we included 10 weight% of ZIF8 into the PES polymer matrix. We can see that circular shape of lumen is produced for the mixed matrix hollow fiber membrane, and the structure of the membrane is somehow similar to the 29 weight% PS, where dense layer is formed on the outer skin, followed by some voids, sponge-like structure, and from the lumen side we can have dense layer and also teardrop structure. We can see that ZIF8 is dispersed uniformly in the polymer matrix without showing any agglomeration. However, it is clear that the ZIF8 is surrounded by macrovoids. This is due to the fact that the ZIF-A and polymer matrix is incompatible. However, to improve the compatibility between filler and polymer, we can functionalize the filler or even do some surface modification to improve the dispersion and the interaction between the polymer and the inorganic filler. But that is beyond the scope of this study. We come to a conclusion that the spinning conditions and also the doped solution formulation are interdependent with each other. This is because the spinning conditions is very, very unique for any doped solution formulation or even the polymer type itself. So we need to identify the accurate spinning conditions to produce the desired morphology and the lumen of any hollow fiber membrane. Before I end this presentation, I would like to acknowledge our sponsors, and if you want to connect with us, the links are provided here. Thank you.
Thank you for the presentation, Mr. Budin. Now, does anyone have any questions on the chat? Okay, nobody seems to have questions. And unfortunately, the presenter is not currently online. And therefore, if anyone has any questions, you can email him directly. Now we will move on to the next presentation by Akihiro Yamazumi. The presenter is supposed to arrive 20 minutes before his or her presentation. Unfortunately, Mr. or Ms. Yamazumi has not submitted any videos nor is present online. And therefore, we will have to skip his or her presentation, but we will still upload his or her presentation or video on YouTube when he or she submits the video. The next presentation, given by Victor Krivenkov, on enhanced two-photon absorption and photoluminescence of semiconductor quantum dots in nano and micro cavities, will be played now. He has submitted a video, so we will play that.
Hello everyone, my name is Viktor Krivenkov. I am a postdoctoral researcher in the Laboratory of Hybrid Photonic Nanomaterials of the National Research Nuclear University, Moscow Engineering Physics Institute in Moscow, Russia. Our studies are dedicated to the design and fabrication of nanomaterials working in the regime of light-matter coupling, even in the non-linear regimes. Here I present you the summary of our recent results about the enhancement of the photoluminescence of semiconductor quantum dots coupled with micro and nano cavities. Semiconductor quantum dots are spherical fluorescent nanocrystals which are known for their unique optical properties. Due to the small diameter, quantum effects are very strong. This leads to a discrete structure of their energy levels and a strong dependence of their absorption and luminescence spectra on the nanocrystal diameter. In practice, quantum dots are attractive for a wide absorption spectrum, not limited to the blue side of wavelength, large values of the absorption cross-sections, and for a narrow luminescence spectrum with a quantum yield that can reach 100%. All that makes quantum dots a promising material for the fabrication of novel nano-hybrid materials for photovoltaics and optoelectronics. One of the most impressive features of quantum dots is their capability for highly efficient two-photon absorption. Two-photon absorption makes it possible to utilize the energy of photons, the energy of which is less than the band gap. Moreover, this process is non-linear in intensity, which determines some of its features, namely the need to use a high excitation intensity and the possibility of three-dimensional localization of excitation by excitation focusing. Indeed, in a laser beam focused by a lens, the highest intensity will be concentrated in the region of the beam waist, and it is there that the highest probability of absorption will be observed. The possibility of three-dimensional localization of two-photon absorption makes this process promising for medicine. In the case of quantum dots, which are used in the field of biomedicine, This also gives us the possibility of using infrared wavelength for biomarkers excitation. Indeed, the so-called transparency windows of biological tissues are located in the near-infrared wavelength range. The use of excitation in the spectral range of these windows allows radiation to penetrate into biological tissues deeper than the other spectral ranges. For this application, quantum dots are significantly better than traditional organic dyes due to the uniquely large two-photon absorption cross-sections of quantum dots. This allows to increase the depth of the detection inside biological tissues further. All that together creates the prospect of using two-photon excitation of highly luminescent semiconductor quantum dots both for ultra-high contrast biovisualization and for fabrication of and design of nano-biohybrid upconversion solar cells and nonlinear optical photodetectors. As I mentioned before, the two-photon absorption quantum dots requires the use of high intensity of laser excitation. However, this is not always possible due to the limitations associated with absorption of radiation by the surrounding medium, especially in the case of bioimaging. Therefore, additional measures are needed to increase the photoluminescence intensity of quantum dots under two-photon excitation. The first way to increase the photoluminescence intensity is to increase the quantum yield of quantum dots. Indeed, when interacting with molecules of the environment, especially in the case of bioimaging, the quantum yield of photoluminescence of quantum dots usually decreases several times due to the appearance of additional non-radiative excitation relaxation channels. In order to increase the photoluminescence of quantum yield, it is necessary to increase the rate of radiative relaxation. This can be done by using the Purcell effect. The nature of this effect is an increase in the density of photon states near the fluor at the wavelength of its photoluminescence, which leads to a significant increase in the rate of radiative relaxation. One of the most promising methods for its implementation is the fabrication of microcavities based on porous silicon photonic crystals. The second way to increase the photoluminescence signal of quantum dots under two-photon excitation is to enhance the local field near metal plasmonic nanoparticles. Indeed, plasmonic nanoparticles can serve as open nanocavities, then can concentrate the electromagnetic field on the nanometer scale. This makes it possible to significantly increase the local intensity of the excitation field and thus significantly increase the probability of absorption for quantum dots located nearby. In this presentation, I'll discuss of both ways. For experiments, we use semiconductor quantum dots with multi-layer shell. Quantum dots consist of cadmium selenide core and 3 monolayers of zinc sulfide, cadmium sulfide, and finally zinc sulfide. The diameter of used quantum dots was about 4.5 nanometers. The maximum of the photoluminescence spectrum was at 560 nanometers, with full width at half maximum of 35 to 40 nanometers. The photoluminescence quantum yield of used quantum dots was 90% in the MXene solution, and corresponding photoluminescence lifetime was 30 nanoseconds. In some experiments we use gold nanorods. They have a diameter of 12 nanometers and length of about 50 nanometers. On the graph one can see the plasma spectrum of the gold nanorods. The longitudinal plasma mode is positioned at the spectral maximum of 800 nanometers, which corresponds to the near-infrared transparency window of biological tissues. From the left top graph one can see that in this spectral region there are no transitions for the quantum dots absorption. Fabrication of porous silicon photonic crystals was performed using the procedure of the electrochemical etching of monocrystalline p-type silicon. Etching was performed by means of a self-made etching setup. The mixture of hydrofluoric acid and ethanol was used as an etching solution. In this study we have fabricated two samples, distributed Bragg reflector and microcavity. Simple reflector was formed by stacking 25 pairs of layers with high porosity of 75% and low porosity of 58%. Porous silicon microcavities were formed by stacking the front and rear mirrors and the half-wave cavity layer which was placed between them. The front and rear mirrors included 5 and 20 pairs of layers, respectively. Note that such type of porous silicon does not demonstrate inherent photoluminescent properties. After etching, samples were thermally oxidized to prevent the strong charge transfer from quantum dots to the silicon surface. Finally, oxidized samples were treated with surfactants in order to make their surface hydrophobic and improve the infiltration of nanocrystals. Embedding of quantum dots into the porous silicon substrate was performed by drop casting of the hexane solution of quantum dots. The photonic band gap of the microcavity was about 150 nanometers wide, with its agent mode centered at 580 nanometers, and its quality factor was about 83. This microcavity design was chosen in order to provide partial matching between the quantum dots emission maximum and the microcavity agent mode, and to suppress the rest of the inhomogeneously broadened photoluminescence, which remained uncoupled. To investigate the effect of gold nanorods on the two-photon absorption of quantum dots, we have fabricated two thin-film hybrid structures consisting of quantum dots in a 20 nanometers thick PMMA layer using the spin coating technique. We chose this thickness because it had been previously shown to be within the optimum range for the maximum photoluminescence enhancement. After fabrication of the initial 20 nanometers quantum dots in PMMA layers, one of two samples was covered with gold nanorods by dropping from aqueous solution and drying the samples, which resulted in the formation of the disordered surface films. At first, we measured the photoluminescence properties of quantum dots in the porous silicon microcavity. One can see that after embedding of quantum dots into the microcavity, their spectra split into two peaks. The first one at 575 nanometers, with width of about 50 nanometers, corresponds to the wavelength of the microcavity aging mode and may be related with the effect of weak coupling of quantum dots with the aging mode. The second peak at 550 has the same width as the initial ensemble quantum dots in the solution and can be attributed to the uncoupled part of the ensemble. In bottom figure, we have plotted the dependencies of peak intensities on the pump power in order to indirectly demonstrate that these two peaks have different radiative relaxation rates. As we increase the pump power, the initially quadratic dependencies saturate and the saturation thresholds was higher for the long wave peak. We approximated the experimental dependencies with the presented equation and found that the observed difference in the saturation thresholds can be only a result of the significant change in the radiative lifetime. Quantitative estimation of the Purcell factor could be made by comparing the radiative relaxation times extracted from the photoluminescence kinetics of the quantum dots coupled to the microcavity aging mode and the uncoupled quantum dots ensemble. In order to exclude the influence of the non-radiative relaxation pathways arising from the interaction of quantum dots with the surface of porous silicon, the control experiment has been made. As control samples, we used quantum dots embedded inside the single black reflector and quantum dots dispersed in the polymer matrix on a glass substrate. The total radiative and non-radiative relaxation rates were calculated. Using the final values, we can estimate the Purcell factor or the radiative rate amplification factor as 4.3. The alternative approach for the increasing of the two-photon excitant photoluminescence is to increase the two-photon absorption probability. Two-photon absorption cross-section is the main parameter that reflects the two-photon absorption efficiency, regardless of the amplitude of the excitation field. Previously, we have shown that the photoluminescence saturation measurements allow finding the two-photon absorption cross-sections of quantum dots in the ensembles without prior knowledge of particle concentration and quantum yield. To describe the saturation, we use the equation that expresses this process as a function of the excitation intensity. In the experiment, we measured the dependence of the photoluminescence intensity on the excitation intensity for two samples. First, quantum dots in the polymer matrix, black squares on the graph, and quantum dots in polymer matrix covered with gold nanorods, red circles on the graph. We fitted these dependencies using the presented equation and found that the highlighted part of the equation was different for these two samples. Assuming that the laser lifetime was the same in both cases, the change is related either to the change in the excitation intensity or to the absorption cross-section. If we use only the far-field excitation intensity, then we need to use the changed effective two-photon absorption cross-section, which change reflects the change in the position of the deflection of the saturation dependence. Thus, we have extracted the two-photon absorption cross-sections from these dependencies on the different excitation wavelength. One can see that the effective cross-sections near the gold nanorods were much higher than the simple cross-sections of quantum dots. Using these values, we have calculated the enhancement of the two-photon absorption, which was up to 12. One can see that the calculated increase of the excitation intensity follows the plasmon spectrum of the gold nanorods, which prove that this enhancement is the result of the plasmon-induced effect. In conclusion, we have investigated the two-photon excitation of quantum dots whose energy transitions are weakly coupled to the aging mode of either porous silicon microcavity or to the plasmon mode of the gold nanorods. We found that inside the porous silicon microcavity, the radiative rate of the two-photon excited quantum dots accelerated by a factor of 4.3. and the two-photon absorption efficiency was increased by a factor of up to 20 near the gold nanorods. As an outlook in the future, one can combine these two effects in one nanostructure, thus sufficiently improving the photoluminescence of quantum dots under two-photon excitation. For details, please read our recent articles on this subject. Thanks for your attention.
Thank you for your presentation, Mr. Krivenkov. Does anyone have any questions?
Okay.
We first have to unmute Mr. Krivenkov. Mr.
Hello.
Krivenkov? Yes.
Hello.
Can you hear us, Mr. Krivenkov?
Yeah, I'm here.
Okay.
Okay. When I see your PPT, I find you use PMMA spin coating with your material. What's the role of the PMMA?
Sorry, what PMMA? What's about PMMA?
Okay.
Sorry?
You use PMMA
Yes.
spin coating with your material, right?
Yes, we mixed PMMA with quantum dots and covered the glass substrate with this film. With film of PMMA with embedded quantum dots.
Oh, okay. Have any question?
There seems to be no other questions. Thank you for your presentation. Again,
Thank you.
Now we will move on to the next presentation by Mrs. or Mr. Irina Kryukova from the National Research Nuclear University of Moscow Engineering Physics Institute in Moscow. And the title is Near Infrared Photoluminescent Hybrid Structures Based on Freestanding Porous Silicon Photonic Crystals and PBS Quantum Dots. And he or she has submitted the video, so we will play that now.
Dear colleagues, nowadays the studies of hybrid luminescent structures with coupled states between light and matter are among the most promising areas in view of observing the effects of increasing distance for resonant energy transfer, formation of polarity and condensates, coherent spontaneous emission, and many other effects. The hybrid luminescent systems based on porous silicon microcavities and lead sulfide quantum dots operating in the near-infrared range present the promising structures for realization of some of these extremely interesting effects. Moreover, an increase in the coupling strength in such structures makes it possible to realize these effects even in one-dimensional microcavities at room temperature. Thereby, one-dimensional porous silicon microcavities, due to their relatively low mode volume, are interesting for creating such hybrid luminescent structures with controlled emission properties. So this was the aim of this study, to create such structures on the basis of lead sulfide quantum dots and porous silicon microcavities. The first component of the hybrid structure, porous silicon microcavity, was manufactured by electrochemical etching of monocrystalline silicon in a water alcohol solution of hydrofluoric acid. During etching, the etching current and, as a consequence, the porosity and refractive index were changed periodically. Hence, the macrocavity structure is a set of layers with top and bottom distributed Bragg reflectors and a cavity between them. There is an image of a macrocavity cross-section on the slide made by scanning electron microscope. To find the optimal parameters of porous silicon microcavity, in addition to data on the silicon porosity, the transfer matrix method was used for calculations. In our case, when the refractive index changes in only one direction and the structure is a set of layers, this method allows to analytically solve Maxwell's equations and simulate the spectral properties of the microcavity. The calculated spectra were in a good agreement with the experimental ones. The second component of the hybrid structure, quantum dots on the base of lead sulfide, were fabricated by colloidal synthesis according to the reaction scheme on the slide. This method allows to control the size of nanoparticles and, as a consequence, the spectral position of the photoluminescence maximum in the infrared range. The previously mentioned porous silicon microcavities were fabricated in 3 steps. First of all, etching of monocrystalline substrate, then exfoliating from this substrate, and finally thermal oxidation. The manufacturing parameters were selected in such a way that the samples preserve the morphology of the structure and their integrity as much as possible. The exfoliated freestanding sample is a thin film no more than 15 microns thick, the surface of which, after thermal oxidation, becomes slightly uneven and bumpy due to the internal mechanical stresses because of the growth of an oxide layer on the silicon pore walls. When comparing the reflection spectra of microcavities, we observe a blue wavelength shift of about 100 nanometers after exfoliation from the substrate and after thermal oxidation. This is due to the change in the effective refractive index because of the growth of the oxide layer and due to a shift in the condition of the quarter wave layers. But in general, the optical characteristics of microcavities before and after exfoliation from substrate and oxidation are well preserved. In particular, the full width at half maximum of the eigenmode and the photonic band gap, as well as secondary peaks in the reflection spectrum. This indicates the absence of critical changes in the morphology of the samples. On the basis of the described microcavities and lead sulfide quantum dots, hybrid luminescent structures in the infrared range were fabricated. The embedment was carried out by dropping quantum dot solution onto porous silicon surface. We have selected the parameters of microcavities in such a way that the eigenmode interacted most efficiently with the exciton transitions of quantum dots, so that the regime of weak coupling between light and matter was established. The straightforward indication of realization of such a regime is the narrowing of the luminescence spectrum of embedded quantum dots. This is due to the Purcell effect, that is, an increase in the rate of spontaneous emission in the cavity, and hence an increase in the intensity of luminescence at the eigenmode wavelength, together with suppression at adjacent wavelength. We observed during experiments a narrowing of the spectrum up to 5 times, depending on the parameters of the oxidized microcavity. Also, by means of confocal microscopy, we found out that in order to achieve a weak coupling regime between light and matter, a low concentration of quantum dots is required. Otherwise, at a relatively high concentration, a quantum dot film is formed on the porous silicon surface, the luminescence intensity of which is orders of magnitude higher than the luminescence intensity of quantum dots effectively embedded into porous silicon. In conclusion, we have fabricated freestanding porous silicon microcavities in the near-infrared range. As a result of exfoliating from the substrate, the sample reflection spectrum demonstrated a blue wavelength shift of about 100 nanometers. Freestanding samples were thermally oxidized in order to reduce the number of recombination channels for the excitation of embedded quantum dots. After oxidation, a blue wavelength shift of 100 nanometers was also observed. In general, the optical characteristics after exfoliation and oxidation, as well as sample morphology, were preserved. After that, lead sulfide quantum dots were embedded into the oxidized macrocavities. In hybrid structure, a narrowing of the luminescence spectrum up to 5 times is observed in comparison with the luminescence spectrum of quantum dots in solution, which indicates the realization of the weak coupling regime between the macrocavity eigenmode and exciton transitions in quantum dots. In our future work, we are planning to create transfer-printed microcavities using the technique of exfoliating porous silicon from the substrate. In this case, instead of etching the entire structure on one substrate, it is suggested to etch the bottom brick mirror and the cavity on the first substrate, then place quantum dots directly into the cavity, and finally cover this structure with the top brick mirror, which was etched and exfoliated from the other substrate. This method allows to precisely control quantum dot distribution and increase their localization in the microcavity structure, which can potentially increase the coupling strength between light and matter. Similar structures in the visible range have already been fabricated by our group, and they have showed excellent luminescence enhancing properties. This study was supported by the Russian Foundation for Basic Research through Laboratory of Nano-Bioengineering at the Moscow Engineering Physics Institute in Russia. Also, the help of Dr. Dmitry Dovzhenko, actually researcher at the University of Southampton in Great Britain, is kindly appreciated. Thank you for your attention.
Thank you for your presentation, Miss Krykova. Does anyone have any questions? No one seems to have questions right now. So thank you again, Irina Krykova, for your presentation. And if anyone has further questions, he or she can send her an email. Now we will move on to the next presentation by Pavel Lenkov from the National Research Nuclear University MEPHL in Moscow. And the topic is nanoprobes based on quantum dots and acridine derivatives for anti-cancer therapy. He or she has submitted a PowerPoint plus sound, so we will play that now.
Hello, dear colleagues. My name is Pavel Linkov, and the title of the presentation is Nanoprobes based on quantum dots and acridine derivatives for anti-cancer therapy.
Sorry, there seems to be some technical difficulties. It will be solved quickly.
Cancer is the second leading cause of death globally and is responsible for an estimated 9.6 million deaths in 2018. Globally, about 1 in 6 deaths is due to cancer. During last century, the cancer treatment approaches have significantly evolved. Target drug delivery and immunotherapy is advanced and not so harmful for the health treatment approaches. Nanomaterials find wide application in modern biomedicine. There are several different methods of delivering drugs in a nanotherapeutic fashion. During last decade, photoluminescent nanocrystal or quantum dots find wide application as alternative to organic dyes in immunofluorescence analysis. In comparison with organic dyes, quantum dots are 100 times brighter and more stable against photobleaching. Quantum dots can be applied as drug carrier in targeted therapy and molecular imaging. We met main task of designing a new multifunctional pharmacological nanoprobe for optical imaging in cancer cells. The multifunctional nanoprobe will comprise pharmacological agents capable to interact with single or double-strand DNA sequences present in a cancer cell, vector group for delivery and internalization of the nanoprobe into cells, and quantum dots for tracking the probe using photoluminescent microscopy. Colloidal synthesis is very popular, effective, and cheap approaches for obtaining monodispersed sample of photoluminescent quantum dots. For the synthesis of cadmium selenide-based quantum dots, we prefer to use hot injection method with cadmium salt or phosphonic acid and triactyl phosphine selenide as precursors, in the presence of oleolamine and triethylenamine as ligands in octadecene solution. This with cadmium salt or phosphonic acid and triactyl phosphine selenide as precursors, in the presence of oleolamine and triethylenamine as ligands in octadecene solution. This approach allowed to obtain highly crystalline core quantum dots with narrow size distribution and tunable optical properties. Biomedical application of quantum dots make specific demands to their properties. I highlighted 3 ones: minimal size, high photoluminescent efficiency, and narrow size distribution in the ensemble. Now let's talk how to implement the requirements, and let's start from the minimal size. In the slide, you can see relationship between the size of the quantum dots and growth time. Typically, quantum dots isolate in the region where the most precursors have just reacted, and the quantum dots are relatively large. For obtaining small cores, we need to overcome 2 problems: fast reaction and huge excess of precursors. For that, we applied fast termination of the reaction with liquid nitrogen and size exclusion chromatography for the core purification. So using liquid nitrogen, we isolate core quantum dots with diameter 1.5 nanometers, and size exclusion chromatography allowed us to purify cores from the excess of precursors, which was in solution and adsorbed on the quantum dot surface. Now let's talk how to obtain quantum dots with high uniformity of physical-chemical properties. Prediction of quantum dots' optical properties require modeling of nanocrystals growth. In the next step, we analyzed the existing models of quantum dots growth and unfortunately found that the typical model based on spherical structure of quantum dots doesn't consider the real geometry of nanocrystals. We proposed a method to build a photomistic model of nanocrystals based on the real geometry of quantum dots and crystallographic data of nanocrystals material. The model based on the 3 key principles. The first, a single cadmium selenide monomers is the starting point of the growth process. The second, quantum dot growth occurs upon the sequential addition of cadmium selenide monomers. And the last one, in each stage of the quantum dot growth, the coordination sphere of the surface atoms is maximally saturated in accordance with the coordination number of the selected atoms. Then we compare our results with literature data. From the figure, you can see the perfect match of our model, blue dots, two-lead data, dash dot line. That confirms the accuracy of our model. Now let's talk how to increase the photoluminescent efficiency of quantum dots. There are two principal approaches to increase photoluminescence efficiency. Increment of confinement potential is restricted by the available choice of the shell material. Increment of shell thickness is restricted by rise of interface strain and the light absorption by the shell material. Using quantum confinement engineering approach, we developed multi-shell quantum dot structure that suggests the highest confinement potential due to alternation of two zinc sulfide layers with intermediate cadmium sulfide layer. Here, thickness of each shell is only one monolayer. This shell configuration provides strong localization of charge carriers in the core and minimal total shell thickness. For the synthesis of the such shell, an extreme accuracy is required. For the precise calculation of precursor quantity, we applied our quantum dots growth model. And for the highly controllable synthesis, we used layer-by-layer shell growth approach. Thus, this result is a proof of the efficiency of the multi-shell structure concept. Then, based on ultra-small cores and multi-shell structure conception, we synthesize sample of core shell quantum dots with photoluminescent quantum yield 68% and total diameter just 3.5 nanometers. Thus, in the result of optimization of quantum dot growth model and new approaches for the synthesis of new cores and core shell quantum dots, we could meet all requirements of advanced quantum dots for biomedical application, and finally synthesize highly uniform and minimal size quantum dots with a high photoluminescence. The next part is devoted to the synthesis of the potential anti-cancer DNA ligand based on acridine derivatives. The structure and stability of G-quadruplex telomerase, a terminal repetitive region of single-strand DNA sequences at each end of chromosome, are of much research interest because they are closely related to cancer. A cancer-specific enzyme telomerase is activated in more than 80% of tumors. Folding and stabilizing the DNA substrate into the non-single-strand conformation using a stabilizing ligand results in effective telomerase inhibition. Therefore, ligand-induced stabilization of telomeric G-quadruplexes has become an attractive strategy for the development of anti-cancer drugs. The target molecule comprises three parts: a heterocyclic acridine framework functionalized with one of three anilines at the position C9 and two symmetrical putrescine side chains at position C4 and 5. It was expected that the planar structure of the acridine would interact with DNA-based pairs, while the aniline would bind to the negatively charged phosphate DNA backbone, and also to bind DNA based for the better stabilization of DNA G quadruplexes. Also, putrescine would increase the solubility of the agent in water and ensure corrugation with the carboxyl functionalized quantum dots. We synthesized, purified, and characterized three gold molecules. Then, to increase their stability, we transformed them into the form of hydrochloric acid salt to ensure better stability and solubility of the molecule in the polar solutions. In the next stage, the biological evaluation of the three acridine derivatives by FRET and TRAP assays was developed. This result allowed us to identify more biologically active molecules, which then were used was used for the conjugation with quantum dots. And the last part of my presentation is devoted to the engineering of multifunctional nanoprobes. Let's return to the state of affairs. We have obtained all components, photoluminescent quantum dots and pharmacological agent, which consist of two parts, vectorization component and DNA ligand. The conjugation of the quantum dots with the acridine ligand we performed in 3 steps. At first, we solubilized the quantum dots with polyethylene glycol derivatives, and then we conjugate the water-soluble quantum dots with acridine ligand with carbodiimide coupling agent, and finally we purified nanoprobes with size exclusion chromatography. Also, we investigate cytotoxicity of the nanoprobes and the components of system by the cell viability assay. Then we investigated uptake of the quantum dots by the human monocytes using scanning confocal microscope. Thus, miniaturization of the quantum dots ensured accelerated penetration through the cell membrane and made ultra-small quantum dots more attractive imaging agent than the regular-sized quantum dots. In summary, based on ultra-small cores, we synthesized core shell quantum dots with advanced optical properties for biomedical applications. Also, we synthesized 3 acridine derivatives capable to interact with quantum dots and with high affinity to DNA G quadruplexes and inhibitory activity against telomerase. And finally, we designed multifunctional nanoprobe based on 2 components and proved its efficiency. Further, we are going to continue in this investigation of properties on more complex biological systems. The work was supported by the Russian Science Foundation. Also, many thanks to my colleagues from the University of Reims Champagne-Ardenne and Moscow University for the assistance in experiments and for the analysis of results. Thank you for your attention.
Thank you for the presentation, Mr. Linkov. Does anyone have any questions? No one seems to have questions. If you have any questions for Mr. Linkov, you can send him an email. Now we will move on to the next presentation given by Zezong John Lee from the University of British Columbia. The title is CO2 Adsorption Potential of Porous Organic Cages for Carbon Capture. And we will play the video shortly. The person, there's a little bit of confusion. Just please wait a few minutes.
Hello everyone, today I'm presenting CO2 adsorption potential of porous organic cages for carbon capture. As we all know, CO2 emissions has been on the rise in the past decades, and finding effective carbon capture technologies has never been more important. Today, I'm presenting a promising carbon capture material called porous organic cage, or POC in short, and porous liquids, which are a type solutions where the POCs are dissolved in the pairing solvent. In this figure, I show the base of octahedral-shaped imine-linked POC cages, and these vertices of the cage base are typically connected to some functional groups to improve the solubility of this cage in the solvents. And the cavity inside the cage base are maintained after the cage is dissolved in the solvent due to size exclusion. Preliminary studies have shown that POCs have high absorption selectivity towards CO2 than nitrogen and oxygen, which was what inspired us to conduct the following work. There are a couple of notable advantages of POCs compared to other sorbent. First, it can be synthesized in continuous flow process as opposed to complex reticular chemistry for MOFs or COFs. And it's also a physio-sorbent, which means it consumes less energy in regeneration. Also, it's liquid-based for a porous liquid, easier to transport compared to solid-based materials. And there are also some disadvantages, such as cage that degrades at high temperature, and the solvent would evaporate at low pressure when, such as low pressure desorption process. So this is a conventional understanding of how the cage molecules absorb CO2, and if you apply temperature pressure swing, the CO2s would be released from the cage cavity. So in this work, we want to look at how this 15-chrome-5 ether substitute amine-linked POC, which is one type of POC in the whole family, how it absorbs CO2 molecules in the bigger picture in more details. Especially, we want to see the interactions between the two types of molecules and what are the absorption sites of this cage and how these sites are sensitive to temperature and pressure. So the functional groups on the vertices are 15-chrome-5 ether in our study, which is shown in flat in this in the right-hand side. So we adopted molecular dynamic simulation using OPLS force field. We selected 20 CO2 molecules and 1 cage molecule inside our simulation box. Sensitivity analysis showed that any number equal or above 20 CO2 molecules would give a convergence in the simulation results. So we just stick with a lower number for efficiency. And these simulations are conducted under MPT from 0.05 ATM to 4 ATM at 300 Kelvin, or 250 to 350 Kelvin at 1 ATM. And during the simulation, the potential energy between the CO2 molecule and the cage molecule were tracked wherever the CO2 molecule is. To represent or to visualize our data more systematically, we reconstructed a coordinate system to center at the center of the cage base, and the 3 axes go through the 3 vertices of the cage base. So we can compare data more systematically. Conventionally, the work done on those POCs were more focusing on the internal site of the cage cavity. But in our work, we expanded the scope of the study to 20 angstrom away from the center of the cage cavity. And we mapped the potential energy and CO2 density in these 4 semicircle areas as representative locations, which are averaged in these 2 plots. As we can see, of course, there's one gas absorption site inside the cavity, but there are 2 other types of sites. One is outside the cage window, and the other is outside cage wall, which are represented by the dashed and solid lines. And these 2 sites are not looked at yet, best to our knowledge in the previous literature. So we are very curious to see more of these. And especially what's interesting is these site 2 and site 3 correspond to the low potential energy locations in the energy mapping as well. That means the high CO2 density clusters are actually enabled by the enthalpic contribution and which we will discuss more later. What's noted here is that by symmetry, there will be one type 2 outside each cage window and a type 3 outside each type wall, so 4 of each type. So for type 2, we see that in this mapping region, which is 9 Armstrong away from the center of the cage base, we see the high CO2 density is typically in the center of this mapping region, which corresponds well with a low potential energy region. That means there's the enthalpic contribution to stabilize the CO2 in this area. What's interesting is that this location is relatively far away from the cage base. So we postulate that the site is stabilized by the van der Waals interactions between the CO2 molecule and the vertex functional groups. So in order to look at the site 1 and site 2 in more details, we plotted the potential energy profile along the two sites, which is actually in the same line. And that line also goes through the center of cage window. So we see quite clearly two potential energy minima. One is inside the cage cavity, which is the typical site 1 adsorption site, and one is outside around 9 Armstrong away, which is the site 2. And this potential energy profile does not change with the temperature and pressure. Here I only show pressure because temperature is the same. And we also plot the CO2 density as the radial distance along the same line. And we see here the quite big peak is the internal site CO2 density, and there's a much smaller peak for site 2. Although the site 2, the magnitude is an order less than the internal site, the larger in number, which there are 4 of those, and the larger in volume may make these sites favorable and interesting. And I will talk about that later in the presentation. What we also noticed is that the peak of the internal CO2 density actually shifts upward as the pressure increases. And we attributed this to inter-CO2 repulsion as the number of CO2 increases in the cage cavity with increasing pressure. And they just feel stronger repulsion to another, so they stay away from the cage center to give more space. And the effect of temperature is similar, that as temperature increases, the peak height decreases for CO2 density. So now moving on to site 3, which is outside the cage wall, we also mapped the CO2 density region, but what we see different is the low potential energy is actually not where the highest CO2 density is, but more toward the vertices. And that's interesting because previously we saw for the window sites, the low potential energy is the same as the high CO2 density sites. So why is this the case? And we compared that with the actual structure of the cage, and we realized that these high, the low potential energy sites correspond to a location of the imine linkage on the cage wall. And the hindrance of those bulky functional groups on the vertices, the CO2 molecules may not be able to move close to where the imine linkages actually are. So they had to find kind of a balanced position, and that's where we observe the highest density. And this is our conclusion on the contributor to the site 3. So we also compare the 3 different temperatures and 3 different pressures of site 3, and we see as the temperature increases or pressure decreases, the CO2 density of site 3 actually changes quite fast and sensitively. So the overall CO2 adsorption sites, as a recap, is one is the internal site, which is commonly seen in literature, and there's another type outside the cage wall, which was contributed by the short-range interaction between the imine groups and CO2 molecules. and one type outside the cage window, which we postulated to be the result of the van der Waals interaction between the vertex functional groups and the CO2 molecules. So far we have identified the sites. How about how effective these sites are? Are the external sites as effective as the internal sites? So we computed the percentage of internally absorbed CO2 molecules to the overall absorbed CO2 molecules in all three sites. And we noticed that especially at high pressure or low temperature, the external site can be quite significant, as in this case, we see 4/5 or 80% of the absorbed CO2 molecules are actually in the external site, as opposed only 20% in the internal site. And the decrease in this fraction means that the external sites are more sensitive to change in pressure and temperature, which will be a significant benefit if we use these cages in pressure or temperature swing absorption, desorption for carbon capture. So people may ask, okay, so far we have only talked about the behavior without any solvent molecules in the consideration. How will solvent molecule affect these sites? And so we did competitive absorption at the presence of solid molecule and CO2 molecule, and we obtained these plots where we do see that the external sites are still there, although at a relatively low temperature. As temperature increases, the external sites becomes less significant, which may be contributed to the stronger entropic factor in the external site at the presence of CO2. But what this also shows is that the thermodynamic drive for these external sites actually exists. All we need to do if we want to utilize these external sites is to probably do better engineers to find stronger functional groups or find stronger enthalpic contributors to stabilize these sites, which of course I'm only looking at one type of cage molecule. There are so many of the family and many more can be engineered, which will be the future interest. So in conclusion, two more external sites are identified for this 15 ether POC for CO2 absorptions. And these external sites can potentially have a greater gas uptake. And these sites are external sites are also more sensitive to temperature and pressure, and thermodynamic drive exists for the external sites even when there are solvent molecules as the interference. So for future, we would, if we want to explore these external sites, we would consider ways to better stabilize them. All right. We acknowledge Compute Canada for provision of high-performance computing resources, and that would conclude my presentation. Thank you.
Thank you for your presentation, Mr. Lee. Does anyone have any other questions for Mr. Lee? It seems that there are no questions for Mr. Lee. Thank you again for your presentation. And the next speaker, Mr. Tongsai Jamong Khan, is not here, unfortunately, and he did not send us any videos nor PowerPoint presentations. Therefore, we will have to skip him. However, you will still be able to view his video if he submits the video to us, and we will submit it to the YouTube. And the same goes for the next speaker, Mr. Kumar, as he's neither present nor submit any videos to us. So yes, that's that. And now we will move on to the final presentation by Mr. Alexei Kisser. Yes, he will be presenting live. Thank you.
Good day. My name is Alexei Kisser. I'm a PhD student of. One moment. I will take my presentation on screen.
Take your time.
Just a moment. Is it visible, my presentation? Oh, okay, I see on the screen. It's okay. And now start. My name is Alexey Kiselov. I am PhD student of Institute on Laser and Information Technologies of Russian Academy of Sciences. And so I got sorry. One small moment. And so on behalf of our research team, I present to your attention the report of controlled optical and electrical contrast caused by reversible laser-induced phase transitions in germanium telluride thin films in spectral range from 200 and 22,000 nanometers. Germanium telluride is a prominent representative of binary hydrogenide compounds of the 4 to 6 groups of chemical elements. That are unique materials, since their properties can differ significantly for two stable phase states, crystalline one state and amorphous state. Germanium telluride thin films, fabricated at room temperature, are amorphous, and the crystalline state, such as rhombohedral alpha germanium telluride structure, is formed at temperatures above 473 to 673 Kelvin degrees. And next phase state as a cubic beta germanium telluride phase is formed at temperatures above 700 Kelvin degrees and absorbed up to 973 degrees of Kelvin. The heating of these films above temperatures of melting, it's about 1000 Kelvin degrees, leads to their melting and subsequent fast cooling returns into previous amorphous state. Owing to their properties, this material is widely used in optical memory devices with high recording density and etc. So, in recent years, these materials have aroused new interest of scientists since it's assumed that they can be used to create optical nanomorphic systems that can combine both memory and logic in one element. Of great interest of applied applications, germanium telluride is the optical contrast in wide spectral range and the high speed of reversible reproducibility and reproducible of the phase transitions. This work, what I will present, the experimental results of laser-induced reversible phase transitions in thin film samples and related with those transitions high contrast in optical and electrical properties, with comparison of these results with results of computational thermokinetic model of fast laser cooling and their subsequent thermoconductive and radiative cooling. Next slide presents motivation of our research. Permanent increasing of information processing volume and speed leads to problems related with increasing the speed of data transporting and processing, with increasing recording density and noise immunity of signals, and those signals resistance for interception improving. Inevitable transition from electrical signal connections to optical ones, and later on the transition to creation of computing device according to the principle of functioning and construction goes to some biological objects. Development and production of optical and electronic computer devices, including using multi-level logic, and all these problems lead to necessity of reaching the next main aims. First, search of relevant materials with the required characteristics and characterization of such materials by optical and electrophysical properties for applications in optical computer and logic devices. On the next slide, to your attention presented process of obtaining and preparation thin film samples. Several series of germanium telluride thin films were obtained by vacuum thermal sputtering on following substrates. One substrate, silicon, to obtain high contrast SEM images, silica glass for main experimental works, and zinc selenide to obtain spectra in wide range of wavelengths. Substrate temperature during growth was 25 Celsius degrees, with grow process controlled by quartz oscillator. On illustration, you can see this analysis of the S-deposited amorphous germanium telluride film obtained on a silicon substrate. Next slide explains basic experimental conception. After impact of laser radiation with energy flux about 38 millijoules per square centimeters, temperature rises above 693 Kelvin with formation crystalline phase state. After another impact of laser-pulsed radiation with flux of 70 millijoules per square centimeters, temperature rises melting point above 998 Kelvin degrees, with, due to the rapid subsequent cooling, forming an amorphous state. Energy fluxes was picked by experiment and proved by comparison with computational model of laser heating. This slide illustrates experimental setup developed to study laser-induced phase transitions. We use this scheme. Its scheme was approved in our previous works. It contains high-speed oscilloscope, pump laser source. It's the second harmonic of ACKNOWLEDGEMENT laser with pulse duration above 10-20 nanoseconds. And we modified laser beam to top hat of top distribution. Next slide, you can see pictures illustrated high contrast in optical and electrical properties of S-deposited, as well as reamorphized by laser and crystalline samples. First, insert the transmissivity and reflectivity spectra of germanium telluride films fabricated on a zinc selenide substrate in the amorphous, as well as reamorphized, and crystalline state, blue lights. So we can see great optical contrast, like in telecommunication range and in near infrared range. So this insert shows us dependencies on the transmissivity and the relative electrical conductivity of germanium telluride samples dependent on the energy flux of rising radiation. To prove phase transitions was developed the XRD analysis. On next slide, we can see some diffractograms of initial target material and some experimental samples. First instant figure R shows the diffraction patterns on the initial germanium telluride powder. The peaks given by the source material can be indexed as the rhombohedral air-free M phase of alpha germanium telluride. This PDF file 00047 1078. XRD studies on insert B have shown that all germanium films obtained on various substrates with grow temperature of 25 Celsius degrees are amorphous. For example, illustration B shows the diffractogram of the germanium film deposited on a CO2 substrate. On the diffractogram, there is no reflexes except for a white halo characterizing the amorphous structure of the molten substrate, which confirms the disordered amorphous structure of the germanium telluride film sample. As a result of impact of laser radiation, the film crystallizes and a metallic sheen characteristics on the crystalline phase appears. On the next figure, figure C, it is shown the diffractogram of the film after a single laser exposure of a flux of 40 7.6 millijoules per square centimeter. The different diagram shows narrow refractions, which indicates the ordering of the atomic structure on the film. Our next insert, figure D, shows us a crystalline sample after impact of laser radiation with energy flux of 72.8 millijoules per square centimeters. And we can see that peaks corresponding to the cubic phase of germanium telluride significantly decreased and became wider as a result of the remorphization processes of this thin film sample. Next slide contains XRD analysis illustration of samples deposited on CO2 and silicon substrates with results of some experimental pulsar impact. For example, the left part related to CO2 substrates and right parts related to silicon substrate. These slides show us results of phase transition dynamics study. To study the dynamic characteristics of phase transitions in germanium telluride thin films, we used experimental setup that I show on this slide. Sorry. Sorry. The change of voltage across the sample associated with the conductivity changing caused by laser-induced phase transitions was recorded by oscilloscope. Laser pulses was generated by a packet of 10 pulses with a frequency of 5 Hz. So for forward transition from amorphous to crystalline state, we obtained next results. Full switch time was above 20 nanoseconds, and for reverse transition from laser crystallized to remorphized thin films, total switching time was about 50 nanoseconds. On this oscillograms illustrating the change in the conductivity of the thin films as a function of laser energy flux on the sample surface. So we can see that we can widely control of electrical properties, and so we can control optical properties of germanium telluride thin films. And the next slide as conclusion. As a result of this research, was shown and proved first the possibility of phase transitions in thin films of germanium telluride under exposure to single and multiple laser pulses with intensity distribution closer to head. This possibility was demonstrated and proved. The high contrast in optical and electrical properties between two phase states was shown, and this contrast can be controlled by dosing of laser energy. High optical properties observed in high optical properties contrast observed in wide range from 200 to 22,000 nanometers. Energy flux for transitions from amorphous to crystalline state lies in range of 7.5 millijoules per square centimeter and observed up to 47.6 millijoules per square centimeter. And for reverse transition, energy flux lies in the range from 47.6 millijoules per square centimeter up to 90 millijoules per square centimeter. These transitions were confirmed by studies of the structural properties of the samples by XRD analysis. Experimental results is well confined by comparison with computational model of laser heating. The possibility of implementing phase transitions in a multi-stage mode is shown changes in conductivity and optical properties in this mode will make us possible to implement a multi-level optical logic and memory. So the total time, as we speak about transition speeds, so the total time of change in conductivity for 100 nanometer thick GTF thin films associated with the laser-induced crystallization processes was about 20 nanoseconds. And reverse conductivity time, changing time was 52 nanoseconds. And some words about funding and publishing. This work was supported by the grant of Ministry of Higher Education and the Russian Fund of Basic Research. In parts, the results of this work was published in Applied Physics Letters and in results in physics journals. And on behalf of our research team, I thank you for paying attention. And if you have any questions, I hope that I will satisfy your interest. Thank you.
Thank you for your presentation, Mr. Kiselev. Does anyone have any questions? I don't see any questions in the chat either. So thank you again for your presentation. And he was the last presenter, so I believe that we are finished with this session. Thank you again, all of you, for coming here. And we genuinely hope that you had a wonderful time. Thank you. Okay, bye-bye.
Thank you.